choose so it says choose appropriate values for n0 and t, and compute DFT of the signal. Okay. As the bandwidth used, the frequency at which the amplitude response drops to 1% of its peak value. Next use 99% energy criteria. All right, so the first thing is, so we need to sample the signal x of t. So this is 8.4, 8.554. And x of t is given 1 plus t squared for every t. Now let me ask you this, did you find the Fourier transform of it? Is that a problem? Do we know what the Fourier transform is?
It's a little hard.
A little hard. I know it's hard, so did you find it or do I need to do it?
I need to do it. All right. So let's take a look at the table.
Which page is the table on?
The pink tab, purple tab, it's like chapter 7. 7.
Or the short?
The short tab.
Okay. These are some properties, but where is the actual table?
702.
702. Okay, cool. All right, so let's see if we have anything here that would allow me to.
Number 3.
Yes. Number 3 says this, that e to the minus a t has a Fourier transform 2a over a squared plus omega squared. This is what we are given. Now, what we need to do is we need to determine the Fourier transform of this one. So here's the x of omega is going to be integral when t goes from minus infinity to plus infinity, 2 over 1 plus t squared e to the minus j omega t dt. That's what I need to determine. What is it that I know? I know that integral when omega goes from minus infinity to plus infinity, 2a over a squared plus omega squared e to the j omega t d omega is equal to the e minus a magnitude t. So if I do substitution here, change the places of t and omega, then from, let me just put the start here. I have something like this. T goes from minus infinity to plus infinity, 2a over a squared plus t squared e to the j omega t dt. I need 1 over 2 pi here, right? Because it's in omega, right? So 1 over 2 pi is equal to e minus a magnitude omega. Okay? So that's the same integral, it's just I swapped t and omega. See that? Now, if I set a equal to 1, then, and I take the complex conjugate of both sides of this integral, then I get something like this. Integral t goes from minus infinity to plus infinity, 2 over 1 plus t squared e to the minus j omega t dt is equal to 2 pi e to the minus a omega. Right? And that's exactly what I need to determine here, right? So my x of omega is equal to 2 pi e to the minus a omega, where a is 1, right? So just omega. So that's the Fourier transform of this sigma. Now they say, well, what is the band? And they give us two criteria. First one is 1% of the maximum. That's an easy one. And the second one is 99% of the energy. Okay? So let's just sketch this x of omega. This is omega. This is x of omega. When omega is equal to 0, this is equal to 2 pi. And then it kind of rolls off this way. Right? So I need to find out, let's say this is part A, this is part B. So BA, I'm going to determine as 2 pi e to the minus BA is equal to 0.01 times 2 pi. In other words, at this BA point, you're going to be at 1% of the maximum magnitude, which is equal to 2 pi. Okay? So from here, I can cancel this, and I get minus BA is equal to ln 0.01, or BA is equal to minus ln of 0.01, which is easily calculated, especially if you have a calculator. So 0.01 ln. So this is 4.6, and it's a radians per second. Okay. Because I'm working in omega, otherwise I have to do everything by pi, 2 pi. So that's the bandwidth, right? So your FA, or let me just say in radians per second, or VA in hertz is going to be VA in radians per second divided by 2 pi. So this is 0.73 hertz. So that's the bandwidth of this signal in hertz. Okay? Everything okay so far? All right. So now it says determine N0 and T. T, I assume, is the how long do you want it sampled, and N0 is how many samples do you want to have, right? Now we need to remember what these two will come from some other requirements. Let's say if I'm going to set Fs larger than 2 times bandwidth, right? Bandwidth is BA here, right? And just to make my life easy, I'm going to say this is 2 times 1 hertz. So I'm going to sample at 2 hertz. Okay? That gives me a little bit of separation, because I'm not sampling at twice the Nyquist, which is about 1.5 hertz, but I'm going to sample at slightly larger. And then the rest one is kind of choose appropriate values and compute DFT. Use 2 different criteria. So the next one is, I guess that you have quite a bit of choice here, right? First I have a sampling frequency, and then the other one is what is it that a resolution that I want to have in a frequency domain. So this is my signal now. This is Fs equal to 2 hertz. This is how it will look like. The repetition from sampling, they need to be on the same height. And this is Fs over 2, which is 1 hertz. And the bandwidth here is 0.73, right, where the signal ends. And the question is what is it that I want resolution to be in a frequency domain? If I say that my F0 is 0.1 hertz, then that gives me T0 of, which is equal to T of 10 seconds. And then the number of samples, N, is going to be T over Ts, or T0 over Ts, which is 10 seconds, dividing by 0.5 seconds, which is 20 seconds. So I'm going to sample every half a second. I'm going to have 20 samples, have a duration of the sampling, which is 10 seconds. This would give me a resolution in a frequency domain of 0.1 hertz, and that's kind of it. Any comments here, questions?
So what are we trying to do to get the appropriate values of N and T0? They give you a lot of leeway.
They give you a lot of leeway, and that's how it's always in practice, right? You just have to, I would probably even go further. I would not even do 20, I'll probably do 32. And then remember the last example I did, that I would trade it for something. I would trade it either for increased sampling rate or maybe for both, to move them apart from one another, reduce aliasing, or I would trade it for a higher resolution in the frequency domain. But I would gain computational efficiency because I'm going to be computing with the power of 2. Right?
So then for B, it's going to be the 0.99 times.
Okay, so part B. So part B, it's only the bandwidth that's difficult here. So how do I do part B? I would say 2 times integral from 0 to b, okay, in radians per second, of e to the minus w dw quantity squared has to be equal to 0.99 times 2 times 0 to plus infinity e to the minus w minus omega quantity squared d omega, right? This is the energy within bandwidth, B, and this is the total energy. Right? You determine total energy by squaring the magnitude response and then integrating underneath. Okay? Now let's 2 and 2 cancels. And then I have integral from 0 to db e to the minus 2w d2w d2w 1/2 is equal to integral from 0 to plus infinity d minus 2w d2w 1/2. What's the value of this integral?
It goes to 1.
It's 1, right? 1. Right? So this whole thing here is 1/2. And so, and then I'm missing something, right? I'm missing times 0.99. So it's 1/2 times 0.99 because I want to capture 99% of this energy in this thing. Now half and half cancels, and this is 1 over e to the minus 2 dB has to be equal to 0.99. Okay? The value of this integral is this. And then from here, you can easily say e to the minus 2 dB is equal to 0.01, or dB is equal to 1/2 of ln of 0.01 and probably minus. So it's 1/2 of this guy. 1 half of this. And then you can kind of continue the same way. Okay? Next question.
Can we talk about the final a little bit? How
Oh, yeah.
the problems
Yeah, that's the whole purpose of today, right? Final is 2 hours, right? I usually budget 15 to 20 minutes per problem. Right? So if you think 2 hours, that's 120. Divide by 20, there's going to be 6 problems on final. And usually, you know, expect, like, I always give them A, B, C, you know, so that kind of guide you through problem. In this problem, I would probably say calculate this, calculate that, assume this, calculate, you know, so that it's easy for you to kind of work through the problem and don't have to wander around. Other than that, it's going to be closed book, closed notes with the formula sheet. There will be multiple groups like last time. There will be, the most important, it will be 2 last chapters. It's going to be this discrete sampling and discrete Fourier transform and the Fourier transform
It's going to be
itself.
like 3 problems for chapter 7 and the other for chapter 8.
I don't know, I haven't made it yet, but it's going to be selected out of the problems that I gave you from homework, right? So.
There is nothing from outside or twisted or something.
It's always going to have a twist, right? But it's going to be usually a twist to make it easier, right? Because a lot of these problems are longer, and then I just cut some piece of the problem to make it manageable in 15 to 20 minute time, right?
When is the final? What day?
The final is on
Thursday.
Thursday, 6 to 8.
This Thursday?
13.
No, not this Thursday.
Yeah, this Thursday.
The following Thursday. A week from this Thursday.
No.
Is that any other?
13th.
Which one?
8.213
8.213.
or 5 an hour.
All right. A signal. A signal is band limited to B hertz, so B is sampled at the rate Fs is equal to 2B. Show that integral from minus infinity to plus infinity x of t dt is equal to t sum from minus infinity to plus infinity x of t. That's part A. And show minus infinity to plus infinity x of t magnitude squared is equal to t sum when from minus infinity to plus infinity x of t magnitude squared. Now this magnitude squared is just to make sure that this is true for complex signals too, but in our case we can remove this magnitude because these signals are all real. Okay, so how did you try it? How would you approach this?
I mean, that looks like the energy, but other than that,
Well, one thing that here's what sampling theorem teaches us: x of t is equal to sum when n goes from minus infinity to plus infinity x of nt times sinc t minus nt, right? Is that the proper formulation? Over t.
because it's time limited.
No, this is the statement of the sampling theorem, right? You get your signal back from its samples reconstructed with a sinc.
zero order whole?
No, this is infinite order force. Remember, this is that reconstruction where you say I'm gonna reconstruct my signal by putting a sink
Right,
over each one of them. Right? So now, what happens if I integrate the left-hand side? I get integral from minus infinity to plus infinity, x of t dt is going to be integral when t goes from minus infinity to plus infinity, sum sum, n goes from minus infinity to plus infinity, x of nt times sinc of t minus nt over t dt. Right? This is what we need to evaluate. And now, if you change the order of this summation, you get an integral from minus infinity to plus infinity of x of t dt is going to be equal to sum when n goes from minus infinity to plus infinity, x of nt, and then integral when t goes from minus infinity to plus infinity, sinc of t minus nt over t dt, right? And now you can see, okay, well, what is this integral? This is the area under the sink, right? How large is the area under the sink? Well, this is equal sum, n goes from minus infinity to plus infinity, x of nt. And let me put t here, and then I say integral when t goes from minus infinity to plus infinity, sinc of t over t minus n dt over t. And, or I can, since I'm integrating between minus infinity to plus infinity, this end here makes no difference, right? It's the area underneath the sink, wherever the sink is, right? And this, according to this, should be equal to 1, right? So you end up with t sum n equal from minus infinity to plus infinity x of nt. Right? So that's this guy. So this one, it was relatively easy to prove. There might be some constants here. I don't know if we need to look at this formula exactly. Because I remember some pi's.
It's pi over t
Where is it?
inside the sink.
Where? Here?
Yeah.
Pi?
It's pi over t, parentheses t minus nt.
Okay. Okay, so that's what I was referring. So it's pi over t, t minus nt, right?
Correct.
Okay, so this is, again, the same thing. Pi over t, t minus nt. And then, again, here. So this is pi over t, t minus nt, dt. And again, here, pi over t, t minus nt, dt, and then this is probably, I need to put here pi,
T over pi.
and this is probably 1 over pi, something like that. So this would cancel all of these.
Where did the t come from in front of the summation?
This one, because I'm making this here look, see I have pi t divided by t. So I have to adjust this d variable here, and then I leave everything outside. Right?
Where did the t come from in front of the summation?
From here, these two cancel each other. See, I have dt here, I have nothing, right? So I divide by t here and multiply by t up here.
Okay.
You follow? And then I have to do same with the pi. Can you look up, in one of the homework problems, we looked actually what is the integral underneath the sink.
This one,
It's not,
it's not one.
no, it's pi, right?
2 over pi.
2 over pi when you go from 0 to plus infinity. But if you integrate over the entire axis, it's probably 1 over pi.
You can check the calculator.
Yeah. Check it, I mean,
Sign it over.
that was one of the problems, remember, we had it for homework, actually. I remember doing it on the board.
We've done so many problems.
That's why it's not zero. That's why it's not zero.
What's the integral underneath the sink?
So the calculator blew up.
Okay. We have this formula, okay, this is on a page, 766. This is the one I remember. Integral from minus infinity to plus infinity, sink squared of kx dx is equal to pi over k. Okay, so that one we're gonna use for the second part. But there was another one that talks about just sink. Integral underneath the sink and sink squared is the same. But I cannot remember where I saw that in this book. So verify, but the process is there, right? You just need to make sure that, you know, some of these constants would cancel each other. Now the second one is more interesting, right? The second part. So we're going to use this, so let's call this A, and let's call this one the B. So here's the second part. Integral from when t goes from minus infinity to plus infinity, x of t magnitude squared dt is going to be equal to integral when t goes from minus infinity to plus infinity, sum when n goes from minus infinity to plus infinity, x of nt times sinc pi over t, t minus nt. Now, everything here needs to be squared dt. Okay, that's what we need to prove. Now, if you square this becomes sum when t goes from minus infinity to plus infinity, and then I have sum when n goes from minus infinity to plus infinity, sum when n goes from minus infinity to plus infinity, x of nt times x of nt, and then sinc pi over t, t minus nt, times sinc pi over t, right, t minus nt, right? Everything here now dt. Okay, this is the square, right? You take the summation here and square. Now I can take the order of summation and integral and reverse this. So this becomes sum when n goes from minus infinity to plus infinity, sum when n goes from minus infinity to plus infinity. These two don't depend on t, so I'll take them outside. So this is x of nt times x of mt. And then I have an interesting thing here. T goes from minus infinity to plus infinity, sinc pi over t, t minus nt, and then sinc, not sine, sinc here. Sinc of pi over t, t minus nt, dt. Now tell me, what is this? How do we call it? sin squared if n is equal to m. But in general, if I take two functions and I multiply them and then I integrate them over some interval,
Energy?
what is it that I'm doing? No.
Convolution.
Let me just, you've seen this so many times. Let's say interval here is minus infinity to plus infinity. And I have a function f and g defined on this interval. And here's what I'm taking. Integral when t goes from t is in interval I, f of t times g of t dt. Right? What is it that I'm doing? Time average of their product. So what is the time average of their product? This is a dot product between two functions, right? How do I take dot product between two functions on a given interval? I multiply them and then I integrate, right? Remember this? Right? So this is how we derive the Fourier series. Fourier series is dot products between sines and cosines and all of that. So here, what I'm taking is dot product between two sinks. Now, the book gives you that as a clue. They say sinks are orthogonal for different time shifts, right? So this is equal to 0 except in one case. And that case is when n is equal to m, right? In which case it's the energy, it's the area under the curve under sink squared. So these two sums collapse into one sum when n goes from minus infinity to plus infinity, x of nt squared, and then t goes from minus infinity to plus infinity, sink squared pi over t, t minus nt, and then dt pi over t, and then here t over pi. Okay? So now this is area underneath the sink squared, right? Where actually I could have just left without this, but this is for k equal 1, right? For k equal 1. Why is k equal 1? Because this is now x. This whole thing is x. And this is also x minus something, right? So what is the value of this integral? Just pi. Just pi, right?
Six squared.
Of this integral here.
Yeah.
Oh.
Because I can write it like this. I can write just this dt, and what did I do? I multiply by pi, divide by t, and then I can subtract minus n pi. Right? I can do that. And this t pi over t minus n pi, I can call that x. And then you see here that I have sink squared of x dx, which is the same as this for k equal to 1. And this is for k equal to 1, this is equal to pi. So this whole thing here is pi that cancels with this pi. So this ends up being sum n goes, t up front goes from minus infinity to plus infinity, x of nt squared.
Where's the n minus pi, or
I can add it arbitrary, right?
minus n pi? Where else do you have to add it to?
Because I want this to be the same as what is underneath the sink. Look what's underneath the sink. If you unwrap this thing here, this is pi over t, t minus n pi, right? So the sink is taken of that. Bring this inside. T and t cancels, n times pi, right? Okay, so that's my, now this is all x.
So sir, this is the check.
Hmm?
This is the checkpoint that we should take care during exams. Get the right answer.
Well, here's what I hoped is this. You look at this and you say, what is this saying? And you should have recognized, oh, this is Parseval's theorem, right? This is our good old friend, right? So you know the answer, right? And then you kind of feel your way through the dark. You're not really, you know, there are no tricks. You know you know the answer, right? And just like I did here, and I said, well, this must be 1. And it is really not 1 because I forgot this pi. But I know that this needs to cancel, right? So that's these are really not. This is not so much of a trick because they gave you this result that sinks are orthogonal, right?
The second one is that sink or sin.
Sink.
Sink. It's always sink.
Right?
There's no
Sink.
sink.
There's no sign, right?
No signs. All sinks.
Send with the
That's
sink.
why it's
Sink.
going.
Sink.
To
Sink.
pi.
Sink. Where do you see sign?
No, I got like, you know, my eyes.
We got cockeyed.
Right.
Problem with my eyes.
So that's a Parseval's theorem statement, and there is always you've noticed that we've had this so many times. By now, you should know that whatever is the power or energy that you can calculate in time domain, there is a formula that is equivalent formula in a frequency domain. And they both look alike. There may be some constants that make the math work out, but essentially the power in the time domain, you're going to square the signal and sum up all the squares, and then there's going to be some Fourier transform of that says take the square of that as well and sum all the squares, and you're going to get the power or energy or whatever is the metric that you're after. And in this case, I'm looking at the power of the signal, which I can calculate, the energy of the signal, which I can calculate directly in the time domain, or I can calculate that from the samples like this, which is a really cool cool result.
I have a question, Professor.
Mhm.
Excuse me. And why we have like summation inside the integrals whenever we want to try to look for in the time to the frequency domain?
Why do we have a summation?
Yeah.
Well, I misspoke. It's not really frequency domain. We are representing our signal as this series. Sorry, forget about the frequency domain at this point. I'm saying I'm representing this x of t as a series here. And if you look at it, this is orthogonal decomposition of x of t. This guy. You know, where I decompose it against this, along these vectors, which are these sinks that are all mutually orthogonal. Right? So what I'm saying here is the power or the energy of the signal is equal to the sum of all the energies along each individual vector. And each individual vector is my sink signal. Right? That's the more abstract view of what is happening.
So this line, like whenever you have this grid on the signals, you treat this like a vectors, right?
Well, I don't have to. It's just one view of the things, right? I can
Because
see.
I'm trying to imagine that.
Well, the way how you imagine is a little bit abstract, right? This is your sink for, let's say, pi over t times t, right? That's the first one. This one is sink, this is the 0th sample. So this is the pi t minus 1. This is the first sample, right?
Right.
And they're orthogonal. Then you have a third sample. This is sink pi over t minus 3t, or 2t, right? 2t. This is your second sample, third sample, and so on. So this is an infinitely dimensional space where every sink that acts as an orthogonal vector. And you're decomposing your entire signal along all of these orthogonal vectors, where each one of them carries each individual sample. So therefore, the total energy of the signal is sum of all of these energies along all of these vector components. That's an abstract view, but just math here is relativistic. Go ahead.
Sir, in practical world, how many this orthogonal signals do we take? Do we take like till half of the power of the actual sink, like fundamental sink, without sampling?
No, why are you, we discussed this with how many Fourier series components you take? Many as you need.
Depends
You
how much
define,
power you
I
have.
want to capture this much energy of the signal. So if you look at the signal x of t, let's say it's an energy signal, therefore, it is, let's just look at it. Here's how you see this signal. Let's assume, for the sake of my drawing on the board, that it's finite in time, right? And that's why it's energy signal. So it starts here, and it kind of goes, let's say this is your signal x of t. So I sample this signal, right? These are my samples. And I have two representations of this signal, which are equal. One is, I say x of t as a time domain function, right? That gives me all the values, implicitly, because this says it's a continuous function of time. Or I can say x of t by the virtue of my sampling theorem, and sampling theorem says that this is true, I can do that, is sum when n goes from minus infinity to plus infinity, just the discrete values, which are these values. But then I have a problem of tails. I need to know what's in between here.
Yes.
So what resolves that? I say, well, in order to get all the values in between, I have to interpolate. And how do I interpolate? According to the sampling theorem, you interpolate using sinc. So you have to take your sample, and then you multiply that by sinc, pi over t, t minus, and t. Okay? Now your question is, how many of these do I need to take?
Yes.
And in this case, I take n from here to here, and after that I don't need it, right? If signal goes longer, I take more, right?
So can we even apply windowing in this? Like first, because the signal
Yeah.
is continuous and we apply
Yeah,
windowing.
if you're doing anything in a discrete domain, like DFT, you have to window. Otherwise, because we cannot, there's nothing that can allow you to process infinitely many samples. So you take this much of the signal, which we call T0, and then we said the basic in this course, what we did is we said we're going to use a rectangular window, just cut here and cut here. In some other courses they told you to round the edges to get less of a spiky response in the frequency.
Isn't the interpolator for the sinc squared, because that would be the triangle, the sinc?
Sync, we interpolate with sync. Remember where is this interpolation coming from? What is this sync?
That's the square.
That's exactly, that's
But I
that,
thought to get the
that's
linear,
that
you need-
filter in the frequency domain, which is cutting the baseband, right? And you're multiplying, this is equivalent,
Convoluted.
remember what we're doing in the frequency domain. This is the sample signal. It's frequently repeated, the repetition in frequency domain. And to reconstruct the original signal, we're multiplying by the brick in a frequency domain, which is convolving with the sync in a time domain.
but this isn't the connecting to the tops with the triangle, which would
No,
have
no,
been the
this is
sinc
perfect.
squared.
This is this thing, remember?
Yeah.
Right? This interpolation, right?
Which is a convolution in the frequency, right?
Which is multiplication in the frequency, which is a convolution in the time domain.
So, but in this case, it's convolution in the frequency, right?
No, it's a
No.
multiplication in the frequency.
X of nt is a constant.
X of nt is a constant. Remember the sample signal, x of t, was some x of nt, delta of t minus nt. And you have to convolve that with a sync, right? So you're convolving sync with the delta, and that only gives you the sync that's time shifted to the position of the delta. So that's where it's coming from. Go ahead.
743.
Are we done with this one?
Yeah. Except for that we proved that there's infinite dimensions with the sinc here in orthogonality.
So,
Well, it depends on the power.
but why does it bother you? I mean, we already had infinite
Because
dimensions.
the math guys will say we've only proved up to the seventh dimension. If we would show them the sinc, then we could say there's infinite dimensions.
But
No, math guys are comfortable with more than, maybe
They're
physics guys have a problem with it.
Physics guys?
With the number of dimensions, but mathematically, you can have, we show that the Fourier series is essentially decomposition of the signal onto orthogonal basis set of the sines and cosines. And how many basis vectors were there? Infinitely many, right? So for us, it's not a big deal. I mean, we don't necessarily, the main problem when we think about dimensions is we always default to this space, right? Well, that's just one example of a space. We can have a vector space that have whatever many dimensions, even infinite, right? So that shouldn't bother us. What was the?
740.
Seven four dash 3. So I say we have two signals, x1 of t, which is equal 10 to the 4 rectangular of 10 to the 4, so let me put it this way, t over 10 to the minus 4. Right? So, and x2 of t, which is delta of t. Notice these two are very similar signals, right? One is, they're both very high and they're both very narrow, right? Are applied to the input of the ideal low-pass filter. So H1 of omega is equal to rect W omega over, I believe this is downstairs, 40,000 pi. And the H2 of omega is rect W over 20,000 pi. Interesting. The outputs Y1 and Y2 of these filters are multiplied to obtain the signal Y is equal to Y1 of t times Y2 of t. Sketch X1 of omega, X2 of omega, sketch H1, H2, sketch Y1 and Y2. Find the bandwidths of Y1, Y2, and YT. All right. So just graphically, I guess this is X1 of t. It goes into this filter. And then you will multiply X2 of t. Goes into the other filter. And this is your H1 of omega, H2 of omega, Y1 of t, Y2 of t, and this is Y of t, which is Y1 of t, Y2 of t. First thing, sketch X1 of omega and X2 of omega. X1 of omega is the Fourier transform of X1 of t. Now, we had in a purple tab, let's see, blue. Okay, there we go. We have, in the blue tab here, we have the Fourier transform, so from table. We have a Fourier transform of rectangular t over tau to be tau times sinc omega tau over 2. That's the result 17, right, in the table.
Is this from the homework or?
Yeah. Yeah.
No, we never got this assigned.
No, I don't think so.
They go up to 7.3 in my notes.
Is it circle?
Let's continue and
Okay, let's just finish it, but I think, it's circle, I think it's one this time. Because it's circle in your book too.
I circle it?
Yeah.
You circled it.
Yeah, it's
You took my book?
Yeah, no, whose book is this? Yeah, so it's circled there, right?
Yeah, but it wasn't.
So, Fourier transform of x1, so let's just put it, so Fourier transform, I have here 10 to the 4 rect of t over 10 to the minus 4, and this gives me essentially sinc omega times tau, which is 10 to the minus 4 divided by 2. So that's the Fourier transform of
So
the
we
first
are
one.
also multiplying it with tau actually.
Wait,
No, because I have 10 to the 4 and times
Oh,
tau
yeah.
gives me 1. Right? Now x2 of omega is really trivial, right? It's a Fourier transform of x2 of t, which is just 1. So sketch these two guys. Well, let me just write this a little bit differently as sinc of omega divided by 2 times 10 to the 4. Okay? So here's how it looks. This is a omega axis for, and this is x2 of omega. So x of 2 omega is trivial. x1 of omega, for a good deal of frequencies, this is close to 1, right? Because it takes, omega needs to get to be, when the sinc becomes 0 for the argument equal to pi, right? So omega, let me just see, when omega over 2 times 10 to the 4 is going to be equal to pi, what is omega? Omega is going to be 2 pi times 10 to the 4. So if I put here 2 pi times 10 to the 4, then here's my, right, and then continues that way. Right, so this is my x1 of omega. So they're flat for a good set of frequencies, right? If you look at everything that is smaller, let's say, than 1 kilohertz, both of them are relatively flat.
Shouldn't it come below the omega line? It's the same
No,
function.
because I'm plotting the magnitude spectrum.
Ah,
Right, so, okay. So that's the x1 of omega. Then it says sketch y, sketch these two guys, right? H1 and H2. Well, this is a rectangular pulse whose width is 40,000 pi. So this is 20,000 times 2 pi, right? So it's 10,000 on each side, right? So if I were to plot this, the first one looks like this, right? It is it's cutting exactly like this. So this is your, and they both go through 1 here, right? So imagine that this is kind of, they're both hitting 1 here. So this is H1 of omega. H2 of omega is having a bandwidth. That is half of the one upstairs. So if I call this point here pi times 10 to the 4, and this is minus pi times 10 to the 4, then the H2 of omega looks like this. All right, so this is H2 of omega. Okay? So that's the second part. what is the next is,
See,
it says sketch y1 of omega and y2 of omega. Well, y1 of omega is the product of these two guys, right? So if I were to sketch y1 of omega, it is just a signal that looks like this, right? This is 2 pi times 10 to the 4. This is omega, y1 of omega. And sketch the other one. It's omega. This is y2 of omega. Well, this is now pi times 10 to the 4. Okay? And the last one is
The bandwidth.
find the bandwidth of y1, y2, and y.
Just multiply them.
No, the bigger
Alright,
bandwidth.
so
is-
let's just say bandwidth of y1 is what? In hertz,
It's 10 to
2
the
pi times
10 kilohertz, right? Bandwidth of y2,
5 kilohertz.
5 kilohertz. And the bandwidth of the product,
15.
beautiful. Yeah? Yeah. Excellent. So you remember, right? Okay. I was afraid they were gonna ask me to sketch why. Because we have to do now, you know, the convolution in the frequency domain between these two ones, right? Unfortunately for me, it was not possible.
Can we look at 7.2.2? I think it's similar to this, but it's a rect of t minus 5 and one of the proof.
Okay, so let's look 7.2.2. This is a good problem for
Exam?
yeah, for the exam.
We'll
Because
present
really there
the
is
rest.
no calculations, right?
Scale the resulting amplitude and phase spectrum.
Oh, it's one of those. From the definition 7.8a, show that the Fourier transform, so we have x of t is given as rectangular for t minus 5. Really? This one is-
Yeah, I was
This one is like really easy, right? So it says, show that Fourier transform of x of t is equal to sinc omega over 2 e to the minus j 5 omega. What is the problem? What is the problem here?
Sketch.
Does it
Yeah,
says
this is-
get the result,
yeah.
amplitude and the phase spectrum? Oh, okay.
Just sketch.
So this we know in general, right? We know that if x of t has a Fourier transform x of omega, then x of t minus some tau has a Fourier transform x of omega e to the minus j omega tau. That's our time delay problem. And remember the physical significance of this one. What this one tells me is that the magnitude spectrum does not change. And that makes sense, because if I build this signal of certain sinusoidals, the fact that I delay this signal cannot change the sinusoidal that I use for building. But it will change their delays. And in the sinusoidal world, if I delay the sinusoidal, it's the same as changing its phase, right? So you get the delay signals by changing the spectrum, and changing the delay and changing the phase spectrum of the Fourier transform. So now, it says sketch this guy. If you remember, let's just do this first. Let's look at the signal x of t, which is rect of t. What is h of omega, x of omega? It is equal to sinc of omega over 2. So this is a Fourier transform. It has a magnitude and a phase. So let's sketch this thing. The magnitude of this guy looks like this.
It looks like sinc squared.
That's magnitude.
That's the magnitude. This is the magnitude sinc omega over 2. Phase which is the angle of x of omega, looks like this. Here, it's 0, minus pi. So this is, and then really you can put it back to 0, but it's customary to do it this way. So it's minus 2 pi here, and so on. So let me use a maybe different color. So that's the signal that is not delayed. So, right, so that's the phase of that guy. Now, let's look at what happens when you delay. Then your magnitude spectrum stays the same. So let me just do here. X of t is rect of t minus phi. Then x of omega is equal to sinc omega 2 over e to the minus j phi omega. So now, this is the same. And then this guy here is actually having, you have to take the phase which is the sum of these two. This is not sinc, it's sinc. Right? So if you look at the phase of this whole thing, let me just say the angle of I can say something like this, A of omega is equal magnitude sinc omega over 2 times e to the j angle x of omega times e to the minus j phi. Right? So you now see that the phase of this one, the phase here, let me call this xd. Right? So angle of xd of omega, d stands for delay, is going to be angle of x of omega minus phi omega. Right? You see that? Because this is now the Fourier transform of the delay signal, Fourier transform of the original signal plus this additional term. And if you represent this one as the magnitude phase, then these two phases add. Right? So now this minus phi omega looks like this. And you need to add these two guys. So what happens here, let's see if I, it's not easy to draw, precisely, but let's say it does this, then there's a jump where it does this, there's a jump, does this, jump, actually, sorry about this, you have to make this like, because the phase of a real signal needs to be off, right? So then it goes like this, like this. So that's the sketch of the phase of the delayed signal. Essentially, sum of this blue line and these steps.
It's a slope.
Go ahead.
Sir, in phase we see like lot of discontinuities at particular points. So
Why is there discontinuity? Because
we have zero.
because you
signal.
switch, right? You go
Yes.
from positive to negative, even though the switch is infinitesimally small, and the sign changes, right? This is smoothed out by the fact that in this area, the magnitude of your signal is very small,
Yes, sir.
right? So the product, the actual, there is nothing weird in the signal. In this place, the signal is so small that the fact that it's plus or minus doesn't matter.
So what effect does it make actually?
Can you hear? Say again?
What does it
What effect does it make?
Physically?
This
Just saying
discontinuity?
how you need to, remember, put on your Fourier series glasses and it says, how do I need to align the sinusoids? And it says, okay, make the phase 0 or make the phase minus 2 pi, right? So just a slight shift, right? That's that discontinuity that you're talking about. It's the fact that we are on a circle,
On a
right?
circle.
So at one point, you just say, hey, this is the end, right? You go back to the origin.
So the
this
slope is
discontinuity-
5?
Sorry.
The slope here is 5. Yeah. 5. Or rather, minus 5.
Is it infinity or finite? For this time, is because the first one you said like,
What is infinity? The space spectrum?
yeah,
Goes forever, right? Because you have a signal that is rect. Rect is the signal that is time limited. Everything that is time limited has infinite spectrum.
oh,
Right, so the spectrum becomes infinite, but it dies, right? You don't have to have all of it. After certain number of lobes, its contribution is negligible. Okay. Anything else?
8.25.
8.25?
Yeah, that was
It's a beast.
It says in example 8.2, the sample of the signal x of t was accomplished by multiplying the signal by a pulse train for d. The procedure is known as natural sampling. Figure 8.25 is called flat sampling of the same signal. Okay. Show that the signal x of t can be recovered from flat top samples if the sampling rate is no less than the Nyquist rate. Explain how you would recover x of t from the flat samples and so on. We show this in general, right? I mean, we're kind of here saying, okay, if it's, oh no. Ah, okay. Ooh. Let's, here's what he's saying. We're saying we have a signal x of t, and we have a sample signal x hat of t that, just for reference, the ideal sample signal is some when n goes from minus infinity to plus infinity, x of n t times delta of t minus n t. This is our ideal sample signal which we discussed. You can never have that, right? So what he's saying now, let's look at this signal, which is sum when n goes from minus infinity to plus infinity, x of nt, pulse of t minus nt divided by some tau. And let me put so that's what he's having here. And it says, well, show that x of t can be recovered from these samples if you are sampling at a Nyquist rate. How would we do that? Any ideas?
The sin squared,
Why sin squared?
linear interpolation.
No,
From the
no,
top to the
no. Do you understand the difference here? there's one thing that we already showed, and this is, the thing that we showed is this, that you can sample, you don't have to sample by delta. You can sample with any periodic function, right? But let me zoom in. We show that you can say x of t times any periodic function, and you get some sample signal running out of sequence here. And how did we show that? Well, this is a periodic signal. It has a Fourier decomposition. We put the Fourier glasses. This is nothing but a whole bunch of sinusoidals that are shifting the spectrum of the signal to the integer multiples of the harmonics. We saw that as a result of this kind of sampling, this is what happens. You know, in ideal sampling, you get, this is ideal sampling, right? You have the periodic repetition of the signal around the sampling frequency. But if you sample this way, then what you have is something that dies, right? Kind of goes like this, right? Because the magnitudes of the Fourier coefficients die, and then these higher order harmonics have a smaller magnitude.
For practical.
Hmm?
For practical.
For practical, it's a matter of fact, this is the only way how you can do it, right?
But we're already sampled and we need to reconstruct it. So we need to
Correct,
pick up
but he's saying here slightly different. We're not multiplying. We're actually taking the signal here, and instead of this pulse here, we're having the square pulse. Instead of impulse, we have a square pulse. The difference is this. If I were to multiply this signal by the bunch of square pulses, here's what I'm gonna, this is called natural sampling. And this is how natural sampling looks like. This is your signal, and let's say these are your sampling times. And just for the sake of argument, sake of illustration, I'm gonna widen these pulses, make them really wide. So your sample signal looks like this, right?
That's what it is.
It's a multiplication, right? So you have this whole, how should I say, section of the signal that's captured, right? Your pulse does not have a flat top. If you do this, however, this is slightly different. This is T, and this is your signal. Now you're doing this, right? And the question is, can you reconstruct the signal if you do this? Obviously, if I let this T go to 0, it becomes small. And then if I put 1 over T here, then I end up having this, right? Because if the tau is finite, the question is how you demonstrate that you can recover. And I need to think about it. I don't know exactly how to prove it, but let's think about what is it that we're doing here for a moment. You are,
See, this is why I mentioned the sig squared, because in the problems before we were doing the first order hold and the 0 order hold, and then they wanted to show that if we integrate.
I remember how we can, we can actually show that this is really, really cool. So, really easy. So let's do this. I'm going to rewrite this in slightly different. I'm going to say that understand this as n goes from minus infinity to plus infinity, x of nt times delta of t minus nt, and what I'm going to say, convolve with pi of t over time. Do you all agree? Because what I'm doing here is I'm representing this as a convolution of the delta pulse and a regular pulse, right? Of the pulse of the wave. Now, now I know what this means in the frequency domain. What is happening here? If I'm convolving in time domain, I'm multiplying two signals in the frequency domain. So what is the Fourier transform of this in the frequency domain?
X omega minus.
It's a periodic extension of the original signal, right? What is the Fourier transform of this one?
again that, but with harmonics which are
Careful,
going
careful.
down.
What is the Fourier transform of this problem? It's a sink.
Sink
What is the, where is the zero of that sink?
at the
One over tau.
1 over tau.
So I'm actually taking this, this signal here is nothing but the original ideally sampled signal multiplied with the sink, right? And then how do I reconstruct? Well, I'm going to reconstruct by putting a low pass filter here. So as long as tau is small enough, right, so that the sink is flat across the baseband of my original signal, the reconstruction is possible. Do you see that?
Yes, sir.
Yeah. So, and then the compromise is really how much of the distortion you have. Well, if the tau becomes, this is 1 over tau. If tau becomes large,
Oh.
then this moves over here, and you start dealing with a sink that will introduce the distortion in your signal, right? So this can be reconstructed. So the answer is yes, you can sample this way and reconstruct the signal provided that this tau is small enough.